So, Mr. Thompson, you're good to go.
My kids always wanted to go see Grammy, so whenever, if they ask, can we go see Grammy? Well, she's working. Well, let's go see her at the store. Or if they try on all the shoes with her, and she'd be introducing them to all of her coworkers.
Okay. So this morning we're gonna go through a little bit more theory, and then later on we finish. We started a question last week that we were supposed to finish. And then we're gonna finish that and do a couple more. All right. So where did we stop last week?
The last
As in,
volume
the
charging.
last question we did, sir?
No, not with the question, with the lecture.
So I think it was volume charges. Sir.
Volume charges. Mhm.
Yes, sir. What's volume charges?
Okay.
You're about to show us the formula for it.
So he said like this.
Yes, sir. I'll check.
So he said, okay. So we said charge distribution is not always a point charge. It can be a line charge, a sheet of charge, or a volume charge. I think we went through well, we went to the point, the line, and the sheet. So here is the volume. So we can have a volume of charge in any form. It can be a cube or a rectangle or a rectangular volume. It can be a cylinder, a sphere. It can be any other shape, right? But like we said at the beginning, we will only be concerned about the rectangular, the cylindrical, and the spherical system, right? So let's look at this basic one now. This is your volume, right? So this is obviously a rectangle. Okay. For your differential volume or the small volume, the differential charge contained therein is rho v dv, where rho v is the charge density, right? So rho v is that differential volume of charge. No, rho v is that volume charge density, and dV is your differential volume. So your electric field or your differential electric field is dq over 4 pi epsilon naught r square AR, right? Which is this, rho v dv if you substitute dq in this equation. So to find your total electric field for the entire volume of charge, you will have to integrate this over the volume. Because like I've tried to stress, all those things like this, the formulas that you memorize, area equal 2 pi r squared, that, you know, volume equal 4/3 pi r cube or whatever. They are all the result of integrals. So the more complete formula then, integrating over the volume, right? So look at the cube. You have length, width, height, which is the volume. So this integral is a triple integral. Right? So so all this is saying, if you have a number of charges, right? The electric field intensity would be due to if you have point charge, line charge, sheet charge, volume charge in a space, the electric field intensity at any point will be due to the contribution from all of them in the same way as the electric field intensity of a number of point charges is the summation. We did this, man. Why you guys wasting time? We did that. We did that, please. I think this was where we stopped. Okay.
Yes, sir.
So here now, we have a circular ring. Like a hula hoop. All right. So we want to find the electric field intensity at some point here. Now, when we tackle a problem like this, never for one moment think that, you know, because we are finding the electric field intensity here, it's for some. That's the only place we can find it. We can find it out here, anywhere. But this is the simplest one you're gonna encounter. if you grow up to specialize in electromagnetic field, right? You can probably get a problem to find the electric field here when you're really proficient at the subject matter. And in order to do that, you probably will take about 5 years to do it. And, at the end, when you're old and gray like I am, you will be awarded a PhD, but you're so close to your grave that it doesn't help you. So we have computer to do these things. But look at the basic. We want to find the electric field intensity at this point P. The reason for we choose that is because we enjoy symmetry and everything becomes simple. So it's a hula hoop, a circular ring of charge, right? We can consider it as a line charge with charge density rho L. So the total charge will be the charge density times the length. So the length is 2 pi r. Okay. So dq is rho L dl. So your dE is rho L dl over 4 pi epsilon naught r squared, AR. Always remember the AR. So what's your R? R is your distance from your charge to the point where you want to find the electric field intensity. Right? So your DL is your radius, small r, d phi. Okay. Let's clarify this. What's the circumference of a circle in radians? That's a question.
And what's a radians?
In radians, sir?
Yeah.
That
2
pi r, sir.
Two pi r.
I mean, yes, sir. The formula wouldn't really change, would it?
No, the formula doesn't change. So the circumference of a circle is 2 pi radians, right? Or 2 pi. There you go. Yeah. 2 pi r radians. So if you want to find a segment, the segment of 90 degrees, it would be 2 pi over 4 radians, right? 2 pi over 4 radians. think I saw it. Anyway, I just say that, yes. Yes. So DL, which would be your segment of the circumference, would be R, and your d phi would be 2 pi over 4. Right? So that's your differential length. Your R times your d phi. In other words, you're not defining d phi, phi as 360 degrees. You are defining as 2 pi in radians. If you look at here, your R, your vector R, would be your radius square plus your height square root of that. That's your R, that's your vector R. R square equal R square, small r square plus Z square. Okay. What are we saying here? Okay. Okay. Now you're here. This is where your differential length is. This is your R. You want to find your field intensity at P due to this differential length. So in order to get to P, look at it like that all the time. You have to go in the minus AR direction and then in the positive Z direction. So your R is minus RAR plus ZAZ. So at all times, when you're asked to calculate the electric field intensity at some point, what should go off in your mind is that this is where the charge is. How do I get to the point where I want the electric field intensity? So from Pythagoras, your vector R is that, and AR is that. And you do your substitutions. Your DE is rho LDL, and your AR is this. When you simplify this mathematics, you come to this. So, or you come to this one. So then, your E becomes the integral from 0 to 2 pi of this. Which works out to this. So this would be the electric field at a point P of a circular ring of charge. So if you go up or down on that z-axis, all you would have to change is the value of z. Because R remains the same to find the electric field. But this,
Sir, so if you go like closer to the edge of the circle, sir, you would change the radius value that you use. Like instead of being vertically above the center of the circular hoop, sir, if you're closer to like one of the quadrants, sir, like in those areas, you would just change the value of the R that you're using.
no. No. Every you just join, not true. Because I think I explained that earlier that if you the reason why we chose along the z-axis, well, is given that the circle is in the xy plane, and we choose the z-axis because it gives us symmetry. If we move away from the axis, right?
No, sir, it was just a hypothetical question, no, sir, to just see if I was like understand the concept or not.
So you want
Understand like the symmetry and how I will put it over the origin.
all right, ask the question again.
I mean, no, it's all right, no, sir, because I can't get it now. I can't get it.
It's not all right, man. Ask the question.
Oh, the question was just, sir, if we weren't in the center of the circle and we were instead in one of the quadrants, if we would just change the R values that we're using.
Well, remember your AR would change, right? Your AR would change, and your Z wouldn't be Z anymore. Because to get from the charge to where you want to go now, you would have to devise a different plan. With me?
Yeah, I got that, sir.
No. This is where life gets good. You know that I'll give you an example now. I think I do this with every class. So I hope I've done it with you. You understand? Okay. Y equal x squared. What's dy by dx? Did I do that with you? It's a little mathematics. Did I do that with you? Answer up, no man. Let me see who got
No,
it.
sir. That's is partial.
Hmm?
Is it to use partial differentiation? I mean, sir.
Differentiation.
Oh,
Y equal x squared. What is dy by dx?
oh, 2x. Yes, sir. I did that. 2x.
Right. So I explained that what happened is that the mathematicians come up with these formula to match things like differentiation, right? So although dy by dx equal 2x for y equal x squared, you know that you got the formula, but you didn't quite understand how it come about. When you understand how it come about, it's a whole different story. Coulomb's law. So we have Coulomb's law. In other words, using the formula dy by dx equal nx to the n minus 1, right? Is much more convenient than go through the actual process of doing the differentiation. In a similar way, this great gentleman, look at Coulomb's law and his experimental results. And he put some formula together to represent. And these formula make life a whole lot easier. So the Gauss law can be used to find E or D for symmetrical charge distribution, such as your point, your line, your sheet, or even your volume charge distribution. Now, it cannot be used if the charge distribution is not symmetric. Goes back to what I was saying. So here are your conditions. I'll read through this. Let's skip something. Because in that, it's not telling you. Okay. Okay, I don't see where they explain what the law actually is. So I'm going to tell you. If you have a charge, and you enclose it, you enclose this charge. The integral over the surface of d dot ds is equal to the charge enclosed. Think of it this way. Say you have a point charge and you enclose it by a sphere. So this charge is radiating electric field. The total electric field that's coming through the surface that you choose is equal to the charge enclosed. The enclosure that you create for the charge, we call it the Gaussian surface. So let's consider a point charge at the origin. That's x equals 0, y equals 0, z equals 0. Right? So what we have learned so far is to find ER by extension D equal Q over 4 pi epsilon naught R square AR.
So the meeting soon finished.
Okay. So like I said, for the point charge, to find E or D at any point, we have the standard formula. E equal Q over 4 pi epsilon naught R square AR. But God said all that is the total charge enclosed, Q, is the charge or the field crossing the Gaussian surface times, well, the field crossing the Gaussian surface, which is Q equal E dot ds or D dot ds. So the only challenge you really have is to choose the correct surface here, right? Because if you have a point charge here, right? Point charge here. And you choose a sphere. No, you choose a cube, right? You're gonna have the electric field on one side. Well, on any side, it's gonna vary, because if your charge is here and you have your cube, right, the electric field at the corner up here is gonna be different from at the side, and so on and so forth as you go around. So you know that the field from a point charge is gonna radiate outward. So the simplest Gaussian surface to work with would be a cube, right? Just give me 1 minute. 1 minute. Okay. So for the point charge at the origin, we choose the spherical coordinate system. So from our earlier vector calculus, the surface area of the differential surface area of the sphere is this, which is equal to this. So your differential surface vector is ds times A normal. So this times A normal. So D, we know that D due to a point charge is given by this. So D dot ds, right? This is your D, and this is your ds. Times D equal this. So you guys have to sit and take your time and make sure you recall the math. So D dot ds works out to that. Okay. So the total charge enclosed is the integral over the entire surface of D dot ds. This is your D dot ds, and this is your surface area of your cube. So Q equal the integral over the surface of D dot ds. What this amounts to is that to find your Q, your D, your E, this is a much simpler approach than to use the long formula with Coulomb's law. Look at this. This is their ds. D dot ds is this. Integral over the surface, D dot ds is this. So Q equal this. So to find D, all you have to do is divide by 4 pi r squared. And to find E, simple like that.
So what is E naught? E naught, that's it, right?
This, that's epsilon naught.
Second, right?
Yeah, man, that's the permittivity of free space. Remember, I explained that in free space, you have a permittivity. If you have a different medium, like water, like gel, whatever your charge is in, as long as the medium is different, then your permittivity changes. So E equal Q over 4 pi epsilon naught R square AR. If it was not free space, your epsilon naught would be replaced by the permittivity of that medium. Usually, the permittivity is represented as a multiple of the permittivity of free space. So, say the permittivity of the medium is twice that of free space, you would have your E would be equal to Q over 4 pi ER E naught R square AR, where your ER would be what you term the relative permittivity, which would, in this case, would be 2, because it's twice times E naught. All right, so when we return at 2, the only thing we're going to lecture on is the infinite line charge, and then we are going to take up some examples. So come prepared for full participation in the working of the problems. I will not just put up the problem and work them for you. You don't learn like that. So come 2 o'clock, prepare to work and ask questions and so on and so forth. All right? Okay?
All right, sir.
Yes, sir.